Should we start? Okay, I'm starting with the lecture now. This was the Reynolds transport theorem expression that we derived yesterday for a stationary, non-deforming control volume. Any doubts to anyone in this expression? किसी को कोई भी doubt, please ask me if you have any doubts. How did we reach this and what is the physical meaning of each term here? Any doubts to anyone? So what does this term?
का फिजिकल सिग्निफिकेंस क्या है?
किस चीज का?
जो n रो v डॉट da वाले.
ये वाला?
Yes sir.
Okay. So I'm coming to this point. Say I had a tank like this, which had number of openings through which fluid could enter or exit. So this was entering the system, this was entering the system, this was exiting the system, exiting, entering, then entering, exiting. So if you consider, wait for a second, if you consider my control volume becomes this one. That is, something is entering into the system, something is exiting out of the system. So now let me know the surface area of this part is this horizontal. The surface normal will be this. Velocity is in this direction. Likewise, surface normal here is this, as well as velocity is in this direction. Surface normal in this case is this, velocity is in the same direction. So if I want to find out what is the total amount that is entering the control volume and exiting the control volume, what should I do? Ask you what is the net mass flow rate exiting from the system, you will say sigma m out minus m in. This is the total efflux from the control volume. यहाँ तक clear है आपको? Now this expression has been written down like this because this expression is simple to apply if you have discrete inlet and outlet points. But for instance, you have something like this, a membrane in which some fluid was entering at some location, some fluid was exiting at some location, and say this at this location, the surface normal will be perpendicular, and say this red represents the surface normals at the locations. So these are the surface normals at various locations. So surface normal is always pointing out. And if I ask you, say the fluid is represented by, say, this blue, fluid is exiting at these points in some other direction. Is that clear? Any doubts? This was the control volume, what you are seeing here. This control volume had many inlet points, many exit points. The blue arrow represents the velocity vector. So blue arrow represents velocity vector. and red arrow represents the area vector. Now if I ask you, this is the control volume, let me know what is the net outflow from this control volume. So what will be your answer? So I mark this as these small areas are differentially small areas. So how will you do this? If these were discrete, then your answer will be, if this was 1, 2, 3, 4, 5, 6, 7. So if these were discrete like this, then you will say that I will take what is the net inlet, what is the net outlet. So you will simply say rho 1, A1, V1. This is entering the system. Then rho 2, A2, V2 is entering the system. Then row 7, sorry, I should put this, row is same, so I take this row only, row A7, V7, then row A6, V6, then row A5, V5. So this is what is entering the control volume. And one side you will write down what is exiting the control volume. So that is row A3, V3, then row A4, V4, then these are the exiting, what are exiting the system. So you know that if this was a discrete system, then this kind of analysis will be sufficient and you don't want to go into the integration part. But had I told you that at each and every point something is entering the control volume and something is exiting the control volume, and direction is also very variable, somewhere it is having this component, somewhere it is moving in this direction, somewhere this direction. So what will you do is you will actually use the integration formula, and if you take any such point anywhere at the periphery on the control volume, what do you know, what is the mass flow rate? Say at this point only, this was the area vector, and say, sorry, this was the say area vector, and this was say the velocity vector. This is the velocity vector, this is the area vector. So for this infinitesimally small surface, you know that the amount of mass that is exiting or entering the system will be equal to what? Rho, what should I write down? Into V into V dot dA. So this is the rate at which the mass is entering or exiting. Whether it is entering or exiting will be dictated by what is the value of this dot product. If the angle is acute, you will end up in net mass exiting the system. If it is obtuse, then it is entering into the system. So this is the rate at which dm dot is equal to rate at which only for this small surface, differentially small control surface, this is the amount that is entering or exiting. Now you want to generalize this, that is, this was only for one point. You want to find out for the entire surface, that is the control surface for this control volume. So what is the way out? You will integrate this to get the total mass flow rate. You will integrate this over what? The entire control surface. And you clear it? And that gives you this thing, rho v dot d. Any doubt? Any doubts to anyone? Who has asked this question?
Sir, हो गया clear, sir.
ठीक है. अब this was for mass. For mass, this was mass entering, mass exiting. If you took momentum, what will happen? By the way, what is small n here in case of mass?
1.
1. What is small n in case of linear momentum?
V.
V. So we have put here a generalized formula, that is there will be n also along with rho v dot dA. Because if it is momentum, this n will be v. If it is mass, it will be unity. You have already seen. If it is unity, then it becomes rho v dot dA. And that is what we have already derived here. So this is the general formula for any kind of extensive property. Are you clear? Hai? So this is the physical meaning of this term. That is, if this was the tank, something was coming in, something was going out. So this something coming in, something going out represents this term. And the rate at which the fluid is increasing is represented by this term. And this term is zero because mass is conserved as far as classical mechanics is concerned. So this equation is equivalently valid for mass, momentum, energy. And clear? Hai? Any doubts? So when I write down this, now carefully help me writing down this for, so this is dN by dt control volume plus surface integral n rho v dot dA. Now when n is equal to m and small n is equal to 1, what do I get? What do I get? This becomes which equation? Continuity equation. When n is equal to mv and small n is equal to v, what does this become? This is named after many researchers, and depending on which assumption you are applying, I can call this as Navier-Stokes equation. This will lead to Navier-Stokes equation. This will lead to Euler equation. This will lead to Cauchy equation. So these we will study, but all the equations, by putting n is equal to mv and small n is equal to v, you can actually derive these equations. So that is the beauty and power of this expression. And if you have n is equal to total energy and small n is equal to energy per unit mass, then this will result in conservation of energy. And in certain cases, you will also know, this is known as Bernoulli's equation. So by deriving a single generalized expression, you can actually derive all the equations in fluid mechanics by changing the value of capital N and small n. Is that clear? Any doubts to anyone? This is the expression for stationary control volume, that is non-deforming. Any doubts to anyone? Now, I told you that we have derived it for the simplest case, that is for this kind of a configuration in which the control volume was stationary as well as it was not deforming. So if you want to extend this formula to these two also, then only there's a little bit of small change in the entire expression, and then that Reynolds transport theorem can be applied to moving as well as deforming control volume as well. So what do you think? What change I have made in the two equations? What change I have made so that now this is valid for
Relative velocity.
relative velocity? So that is the only change. So please remember this. Everything else is same. Only in this V, I have V relative now. And you clear है? V relative means if this was the control volume and this was the control surface, अगर तो स्टेशनरी होता then you know that अगर कोई यहां से fluid is coming out, this is stationary, जो भी इसकी velocity होगी मान लो 1 मीटर पर सेकंड है, तो इसका मतलब क्या हुआ, ये 1 मीटर पर सेकंड ही है. लेकिन मान लीजिए ये खुद कंट्रोल वॉल्यूम इसी डायरेक्शन में, ये खुद कंट्रोल वॉल्यूम इसी डायरेक्शन में 0.5 मीटर पर सेकंड से मूव कर रहा होता, तो आप क्या लेते हैं इसको? खुद कंट्रोल वॉल्यूम भी 0.5 मीटर पर सेकंड से मूव कर रहा है, तो व्हाट डज दैट मीन? फिजिकली भी सोच के देखिए, अगर ये भी 0.5 से मूव कर रहा है, इसमें से फ्लूइड 1 से कर रहा है, फ्लूइड की एब्सोल्यूट वेलोसिटी 1 दी हुई है, तो इसका मतलब रिलेटिवली तो सिर्फ 0.5 से बाहर जा रहा है फ्लूइड. So that's why we have relative velocity here, if it is moving or deforming control volume. So this is the only difference you will include if you are going from stationary non-deforming to moving deforming. And that should be very carefully executed. Any doubts to anyone? Any doubts to anyone? Now I'm coming to one small aspect, that this equation in many textbooks is written in this format, and you will see that format in most of the textbooks, and you should understand that why it is so. Any doubts in this expression? ये clear है सबको?
Yes, sir.
Now this thing, now what is n? Generally n is, you know that n upon is equal to small n. So what does that mean? N can be written down as n into m. Are you clear hai? And this can also be written down as n rho dv. Any doubts to anyone? किसी को कोई डाउट इस एक्सप्रेशन में? किसी को कोई भी डाउट इस एक्सप्रेशन में? I should. So n can be written down as triple integral n rho dv. ये क्लियर है? मैंने m को rho dv लिख दिया. This is n is property, extensive property per unit mass. So this has come from this expression. Any doubts to anyone? Any doubts to anyone? So now what does this expression become now? D by dt control volume n rho dv. ये clear है? This expression can be written down like this. Clear? Now please try to see. I am writing down this as triple integral control volume curly by curly t n rho dv. That is, I have taken this sign in the integral and the total derivative has got converted to a partial derivative. So this kind of transformation is only possible if the control volume is stationary and non-deforming. And I will let you know why. Now this example will help you to understand this. Say these are two curves, that is, a function is represented which is this blue curve at some time t, and which changes its position at time t plus delta t, and it becomes like this. But what is not changing is, what is not changing? The limits are not changing. So this is the function that you are analyzing, and the limits are from a to b. And after time t plus delta t, you are analyzing the same function which has now changed to some other value, but the limits you are analyzing is still the same. Are you clear? Any doubts? So if I ask you what is f x t integral dx, what will be this equal to? f x t.
सर ए से बी के बीच में एरिया.
So this blue area, ये clear है? And what will be f x t plus delta t integral?
सर ये जो ब्लैंक पोर्शन है वो वाला.
ये total. Are you clear? Any doubts? Now if I ask you what is this? d by dt integral f x t dx from a to b. What will be your answer? My question is, you know that integral fx t from a to b is this blue area, and fx t plus delta t from a to b is this yellow area. Now my question is, what is d by dt a to b fx dx? What is this? Now, can I take this differential inside the integral or not?
Yes, sir.
You can take, because limits are not function of time. They are not changing with respect to time. So when you take this inside, how can you take this inside? What is the definition of a derivative? What is the definition of a derivative? Limit
Change of with respect to time.
limit delta t tends to 0. What should I write down?
F of x plus delta t.
Integral a to b f of x
X
t plus delta t
minus f of x delta t
f of x t upon
delta t.
delta t, and this is dx. Clear? Any doubts? Now by Taylor series expansion, what do you know about this term? What is this? fx t plus delta t equal to, by Taylor series expansion, fx t plus, what should I write down? Curly f by curly t, what should I write down? Delta t plus curly square f by curly t square delta t square by 2 factorial. ये clear है सबको? This thing. Any doubts? Any doubts to anyone? So if you substitute this term here, what do you get finally? What do you get finally? You get d by dt integral a to b fxt dx. This becomes equal to, so please see, this term gets cancelled with this, and
So
you can
how is it
Hani,
written?
how is it? Which expression? ये वाली? हाँ जी, प्लीज, क्या पूछ रहे हैं आप? हेलो,
सर मतलब ये कैसे आया?
कौन से वाला?
नीचे वाला से f of x t plus delta t in the form of f of x t plus del of.
Okay, so you have studied Taylor series or not?
Yes sir, Taylor
What is
series.
this equal to?
So we have used the expansion of that.
Taylor series expansion.
Yes, sir. Yes, sir. Yes, sir.
Clear?
Yeah, got it.
So this is the Taylor series expansion, and there is a curly because Taylor series is being expanded with respect to time. Although f is function of x as well as t. So that's why you have a curly instead of the total derivative. Is that clear?
Yes, sir.
So you know that the small term can be neglected, this term can be neglected as delta t goes to 0. And you are left with only these two terms. So out of which this term will get cancelled with this. And then what are you finally left with? So you are left with a to b, or I should say limit delta t tends to 0, a to b, curly f by curly t delta t. This was upon delta t, if you remember. So this was upon delta t because this has already got cancelled. So as limit delta t tends to 0, what will this fraction tend to? As delta t tends to 0, what will delta t by delta t tend to? Hanji. What will delta t by delta t tend to? 1.
1. Yes, sir.
So what do you get? This becomes equal to a to b curly f by curly t dx. So this term has got converted to this term, that is the ordinary derivative got converted to partial derivative. This was only possible. Why? Because limits themselves were not changing with respect to time. If these were changing, you will not get this simplified formula. So please remember, when in the Reynolds transport theorem, I write down this as this simply reminds me of the fact that limits are not changing. The example I gave you was a one-dimensional example, that was, it was only function of x, but here it is a volume, so it is function of x, y and z. What does that mean? The limits of x, y and z are not changing. So what does that mean? If the limits are not changing, it means it is stationary as well as non-deforming. And that's why I can write down this term as this term. So please remember, you cannot make similar conversion here, because here a and b, or the limits of x, y, z are not constants. They are changing with time, because as the volume will change or as the volume will move, the limits of integration will change. So that is the problem with this. So this is applied only in this special case. Otherwise, these formulas are general. Then you will not convert the ordinary derivative to partial derivative. Are you clear? Any doubts to
Yes.
anyone?
So there was just one doubt, that why have you neglected the double differentiation of f of xt
Okay, this term?
in the, yes, sir, last term. We said it tends to 0. Why
Yes.
so?
Yes. So if delta t tends to 0,
Yes, sir.
अगर मान लीजिए, say for instance delta t was say 0.05, what will be delta t square then?
0.00025.
So this term will be much smaller as compared to this term.
Yes, sir.
So I can neglect this term.
Okay.
So it is by that. So you should always write down here, I should be much more correct. It should be always approximately equal to, because this will never be equal to these two, because this is an infinite sum.
Yes.
But this infinite sum becomes equal in approximation to this when delta t is sufficiently small. Are you clear? So this is the Reynolds transport theorem as applied to two cases, whether it is stationary and non-deforming control volume, or moving and deforming control volume. So this should be very clear in your mind. Any doubts to anyone? Any doubts to anyone in any of the terms?